Welcome back, everybody. This is our third session in JEE Mains previous year questions for chapter Alternating Current. Before this video, we have made two videos in this series, and all of those videos are available on our YouTube channel. We have also started a similar series for NEET previous years. So if some of your friends are preparing for NEET, then you can guide them through those videos also. And if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. Also, if you find these videos useful, then do press the like button, share it, and subscribe to our channel. With this, let's start today's video. In the previous one, we completed around question number 15 or something. This was the last question number 30. And today we will start with question number 15. So a coil of self-inductance 10 millihenry and resistance zero point 0.1 ohm is connected through a switch to a battery of internal resistance. So we have a battery of internal resistance 0.9 ohm, and we have a inductor 10 millihenry and resistance and a additional resistance of 0.1 ohm. The time taken from the current to attain 80% of the saturation value, and we have been given a value of Ln5, that is 1.6. So let us first draw the circuit diagram here. We have an inductor with a resistance of 0.1 ohm, and then we have a battery with internal resistance of 0.9 ohm, and they are connected in the circuit. Now this whole circuit can be represented by like this, that we have an inductor and we have a total resistance of 0.1 plus 0.9, that is 1 ohm, and we have a battery here, and inductor is of 10 millihenry and battery we don't know, so suppose battery is E. Now it is asked time taken to attain the 80% of the saturation value, and this is the current flowing through the inductor. We know that in an inductor, current slowly builds up to a certain value and then it stops changing. And for inductor, the charging equation of current is given by I is equal to I node 1 minus E minus T by tau, where tau is the time constant. It is given by L by R. So here current is 80%. So I is 80%, or 80 by 100 of I node is equal to I node times 1 minus E minus T by tau. I node get cancelled, 0 cancelled, and we have 4 by 5. So 4 by 5 is equal to 1 minus ETT by tau, and further E minus T by tau is 1 minus 4 by 5, or 1 by 5. Taking antilog of both of side, natural antilog, so it will be minus T by tau is equal to minus ln of 5, because ln1 is 0, so minus get cancelled, and time is tau into ln 5. Tau is L by R. L is here 10 millihenry, so 10 into 10 raised to power minus 3 divided by R. Value of R is 1 ohm. Combined resistance is 1 ohm. Multiply ln 5, that is 1.6. So this will be basically 1.6 into 10 raised to power minus 2, or 0.6 0.016 seconds. That is option D for us. Let's move to the next one. A 20 Henry inductor coil is connected to a 10 ohm resistance in series as shown in the figure. The time at which rate of dissipation of energy joules heat across resistance is equal to rate at which magnetic energy is stored in the inductor. So here we have been asked the two terms. First is rate of dissipation of energy across a resistance. Now we know that heat produced inside a resistance when some current flows through it, that heat is given by I square R into T. As we have been asked rate of dissipation energy, so it will be dH by dt, and that will be equal to I square R, and basically it's the power of the resistance, and that will be again equal to I square R is also equal to V square by R, and the rate at which magnetic energy is stored in the inductor. Now energy stored in inductor, that uh, that U, it is magnetic energy, and it is equal to half Li square. And we have been again asked the rate at which magnetic energy is stored, so we have to again find out du by dt, and that will be half L into derivative of I, because only current is changing here with time, so twice of I into di by dt, so it will be Li di by dt. Now, as per mentioned that both of these terms are equal, means this rate of energy dissipation across resistance is equal to rate of energy build up or dissipation across the inductor. So both of these are equal, means Li di by dt is equal to I square R. I gets cancelled from here, and we get L di by dt is equal to IR. Now, this L di by dt is the potential difference across the inductor, a potential drop across the inductor, and IR is the potential drop across the resistance. From this, we can see that potential drop across both of these resistance and inductor is equal. Now, as we have to find out the time here, we have to calculate, we have to find out the time, so we cannot integrate it, because if we integrate this whole formula, then we will get an average value. In the one side we will get we can say current, and in this other side we will also get current, because current is I is dependent upon the time. So what we will do here, we will write the equation of the current flowing through the inductor, because the same current is flowing through the whole circuit. So, and we know that when current flows through the inductor, then it follows this equation that I is equal to I node 1 minus e t by tau, and from this we can calculate its derivative. So di by dt will be I node my 0 minus e minus t by tau into minus 1 by tau. So that will be I node e minus t by tau divided by tau. Now we will substitute both of these values here in this one. So we will get L I node e minus t tau divided by tau is equal to I node 1 minus e minus t tau into R. Now I node get cancelled, and further this tau is equal to L by R. And if we bring this R here, so it will be again L by R is equal to tau by tau. So we will be left basically minus Et by tau is equal to 1 minus E minus T by tau, as this R coming in the denominator, L by R is equal to tau, and tau will get cancelled from each other. So further these two terms will add, so it will be twice of E minus T tau is equal to 1, or E minus T tau is equal to half. Taking antilog of both of these sides, we will get minus T tau is equal to minus ln 2, and minus negative sign get cancelled, and time is equal to tau times ln 2. Tau is L by R, L is 20, R is 10, so 2 ln 2, that is option C for us. Let us move to the next one. So here a circuit connected to AC source of EMF value is given to us, with t in seconds gives phase difference of pi by 4 between the EMF and the current. Which of the following circuit exhibits this? Now it is mentioned that phase difference is pi by 4 between the current and the potential. So we can say phi is pi by 4, and for phase difference we have a relation that tangent phi is equal to XE minus XL divided by R. So what we will do here, we will calculate one by one using all of these values. So in the first one we have resistance and inductor with 1 kilo ohm resistance and 10 millihenry inductance, and omega will come from here. Omega is equal to 100. So in the first one, tangent phi, as it should come pi by 4. So we don't have in capacitor here, so it will be negative. XL is omega times L. Omega is 100 and L is 10 millihenry, so 10 into 10 raised to power minus 3 divided by resistance, that is 1 kilo ohm, or 10 raised to power 3. So if we solve this, we will get something like negative 10 raised to power 6 and 9. So this is not the required one, because here phi is already mentioned, it is pi by 4, so tangent phi should be equal to 1. So option 1 does not fit. Coming to the second, 1 kilo ohm and 1 millihenry. So in that case, in the second case, tangent phi will be minus 100 into 1 into 10 raised to power minus 3, again divided by 10 raised to power plus 3, and it will again go to negative 10 raised to power 3, 6 to 8. So again option B is rejected. Coming to the option 3, here we will have tangent phi is equal to, here we have been given capacitance, and for capacitance we will take XC, and here XL will be 0, and XC is 1 by omega C, so it will be 1 by omega C divided by R, or 1 by omega CR. Now substituting the value, omega is 100, C is 1 microfarad or 10 to the power minus 6, and into we have resistance of 1 kilo ohm or 1000 here. So this will be 1 by 10 raised to power minus 1 or 10. So again option 3, option C, I think it is C, it should be C. Option C is also rejected. And coming to the fourth one, here tangent phi, again we have resistance and capacitance, so tangent phi will be 1 by omega CR. So it will be, now omega is 100, capacitance is 10 microfarad, so 10 into minus 6, and resistance is 1000. So 1000 multiply 1000, 10 raised to power 6 into minus 6, so 1 by 1 or 1. So this is the required values for obtaining phase difference of pi by 4. So option D will be the right answer here. Let's move to the next one. In the figure shown, the circuit contains two identical resistors with resistance R is equal to 5 ohm and inductance with L equal to 2 millihenry. So here as per mentioned that we have two identical resistance of 5 ohm and this is also 5 ohm and this is of 2 millihenry or 2 into 10 to the power minus 3 Henry. An ideal battery of 15 volt is connected across the circuit. So this battery is of 15 volt. What will be the current flowing through the battery after long time the switch is closed? So after the long time, what happened that after the long time, the current in the circuit will become stable. And if current in the circuit becomes stable, we know that across inductor, potential drop across the inductor is given by dl L into di by dt. And if current is stable, means I is constant, so this whole term will reduce to 0. Or we can say, after a long time, inductor act as a short circuit, or it gives a free path to the current, and then our circuit will reduce to something like this, that we have a battery here, we have a resistance of 5 ohm here, and we have another resistance of 5 ohm here. 15 volt battery, 5 ohm resistance, 5 ohm resistance. So as both of these 5 ohms are in parallel, it means they will give us combined resistance of 2.5 ohm. So our final circuit will be something like this, 2.5 ohm. So this is the final circuit with 15 volt battery. And now current in this circuit will be given by potential by the resistance, that is 2.5, and it will be 25 15 25 into 10, so 2 5 3, that is 6 ampere. Option D is the right answer here. Now let's move to the next one. In the above circuit, C is root 3 by 2 microfarad, R is 20 ohm, so this is root 3 by 2 into 10 to the power minus 6, R2 is 20 ohm, L is root 3 by 10 Henry, and R1 is 10 ohm, and the current in the lower path is I1 and in the upper path is the I2. The voltage is 220 root 2 sine 100 omega t, 200 root 2 sine 100 t means this is the peak value and this is the omega. The phase difference between I1 and I2. So we have to find out phase difference between I1 and 2. So to calculate the phase difference, what we will do here, we will we can say we will take both of these part I1 and I2 as an individual circuit or as a separate circuit, and across both of these circuit we have applied the same voltage. So what we will do, we will first calculate for the I1 and then we will calculate for the I2. So let for the I1. Now we are doing calculations for I1. For I1, to calculate the phase difference with respect to voltage, here you have to be very cautious that one is an inductor circuit and one is a capacitor circuit. So both of them will give phase difference in different directions. So let first start with inductor circuit. So in inductor circuit, normally what we have, I lags behind voltage, and that angle will be given by tangent phi will be given by XL by R. XL is omega L into R. Omega is 2 pi times frequency, or we can say omega is directly given to us, that is 100. Here omega is 100 already available. So 100 multiply by the L value, that is root 3 by H, root 3 by 10, and resistance in series with it, that is 10. So this will be root 3, or we can say phi 1, that is the angle between current flowing through an inductor or current flowing through this path and the voltage, applied voltage, that will be 30 degree, I think. Oh, sorry, 60. Tangent 30 is the root 3 is 60 degree. So it will be 60 degree. Now for the I2. Now in case of capacitor, current, or sorry, not current, potential lags behind current. Means here current is ahead of potential. In previous case, current was behind of the potential. And in this case, the angle tangent phi 2 will be given by XC by R. So that will be 1 by omega CR, because XC is 1 by omega C. So omega is 100, C is root 3 by 2 into 10 raised to power minus 6, and here R2 is 20. So it is 20. And now if we do the calculation, it will be 10. So tangent phi 2 will be, this is 100, 10, both of these will give us 1000. 1000 in multiply 10 raised to power minus 6, that will be 10 raised to power minus 3, or tangent phi 2 will be 1000 by root 3. Now we know that graph for tangent is something like this. This is the value, and here we have theta. So as we approach 90 degree, so it almost goes to infinite, and this is also very large value. So here from approximation we can write that phi 2 will be approximately to the also equal to the 90 degree, because this is a very large value. Now let's draw the diagram to get the idea of what will be the angle between both of these two. Suppose our x-axis represents our potential. This is our potential. Now our current I1 lags behind it by 60 degree. So if I1 lags behind by 60 degree, so suppose downward direction is the behind direction. So this angle is 60 degree and this is I1. Then I2 is at the 90 degree and it is ahead of voltage. So it will be here, something here. So here we will get I2 and it will be ahead of potential by 90 degree. So the angle between both I1 and I2 is 150 degree here. So angle is 150 degree between I1 and I2. And if we match options, none of the options match here. None of the options match here means there is some mistake in the option, or it could have been 150. This 0 could have been 150. Then it would have been the right answer. Now let's start. Let's move to the next one. Here we have a circuit shown. So let me adjust it first. Here we have a circuit. The switch S1 is closed at time t is equal to 0, and switch S2 is kept open. So S2 is open and S1 is closed. After some time t node, the switch S1 is opened and S2 is closed. The behavior of the current as a function of the time we have to find out here. So let we will solve it in the two cases. So case 1, when S1 close and S2 is open. So in that scenario, what we have, our circuit will reduce to, we have resistance here and inductor here with S1 is S2 is open, so it is not a part of circuit, and we have a battery here, and this will be the connection. So in this circuit, we can see that our inductor will charge, and when inductor charges, it charges slowly, and its charging equation is given by I is equal to I node 1 minus E minus T by tau. And if we plot its charging current, then it is given by something like this, that its charging current slowly builds up and then reach to a saturation value. So this is the, we can say, charging part. Here we have current and here we have time. Now coming to the second part, that case 2. Here we have S2 close and S1 open. Now if S2 is closed and S1 is open, then battery is out of the circuit, and our circuit will reduce to something like this, that we have a resistance here, we have an inductor here, and they are connected in such a way. Now, initially, due to this battery, this inductor was charging. Here, this was case of charging. And now, as there is no battery in the circuit, and initially it stored some energy, so it will be now discharging. So this state is a state of discharging, and we know when an inductor discharge, its discharging equation is given by I is equal to I node e raised to power minus t by tau. And if we plot this charging behavior of inductor, suppose this is the point at which inductor starts discharging, or we can say time is equal to t node, then after that it will follow this curve like this. So this is the charging part, and this is the discharging part. And if we try to match the answer here, here in option C and D, the charging is given straight, means there is linear charging. And we know in case of inductor, the charging is not linear, charging is exponential. So both C and D gets rejected. In option A, charging is exponential, and in option B, charging is not, we can say, completely exponential, but it's following the curve. So in both in A and B, charging part is right. Now coming to the discharging part, in option A, discharging is shown as a straight line, means the discharging is linear. But we also know that again discharging is exponential here. So option A is rejected. So the only available option that we can mark, that is option B here. So let's move to the next one. An AC circuit containing an inductor of 20 millihenry, capacitor and resistor driven by a voltage source of 50 Hz 24 volt. The energy dissipated in the circuit in 60 seconds is. So what we will do here, we have to first calculate the power of the circuit, and then we can multiply that power to the time of 60 seconds. Then we will get the value of energy dissipated in the 60 seconds. So this is a series circuit. So diagram will look like something like this, that we have an inductor, then we have a capacitor, and then we have a resistance, and we have a battery here. Sorry, not battery. It is an AC source of 20 volt and 50 hertz. So we have to calculate the total impedance of the circuit. Total impedance of the circuit Z is given by R square plus XC minus XL square. So first we know the value of R, that is 60 ohm. So let's calculate XC. XC is given by 1 by omega CR. So omega is 2 pi times the frequency, or 2 pi times 50. Capacitance is 120 into 10 raised to power minus 6. And oh sorry, XC is 1 by omega C. There is no R. That is XC by R, or tangent phi. So this is omega XC, and solving this, we will get something around 26.5 ohm. Now coming to XL, XL is omega times L, so that will be 2 pi times frequency, that is 50 into L, that is 20 into 10 raised to power minus 3. So 50 into 2 is 100, and that will 100 into 0, 1000. So 10 raised to power minus 3 is cancelled, and we are left with 2 into pi. So 2 pi is 6.8 ohms, that is XL. So now let's calculate the value of Z, or impedance. So Z will be R square, that is 60 square, so 3600, plus 26.5 minus 6.28 whole square. Now this is 26.5 minus 6.25, so it is almost 20, so we assume that it will be 20. So 3600 plus 20 square is 400. Now we are approximating it slightly. So it will be 4000 under root, or we can say 20 root 10. This is the value of impedance. And now, as we have to calculate the energy dissipated, and energy is equal to power into time. And now power is voltage into current into cos of phi into the time, that is 60 second, of course. And further, we can write current as potential by Z, so it will be V square by Z into cos of phi into time. So now V is 24, so 24 multiplied 24. Now Z is 20 root 10. Cos of phi is R by Z, so R is 60 here, and 20 root 10, and time is, again it is mentioned to be 60 second. So this 20 will on 3, this 20 on 3, 10 root 10 into root 10 is 10. So what we are left with 24 multiplied 24 into 3 multiplied 3 divided by 10, I think. So this will give us 5184 divided by 10, or 518.4, and we can write it like 5.18 into 10 raised to power 2 joule, and that matches with option C. So with this, we end this video here. Hopefully whatever we have covered is helpful to you. Again, if any doubts or suggestion, you can put them in comment section. I will try to resolve them. And if you find this video useful, helpful, then do press the like button, share it as much as possible, and subscribe to our channel. Also, if you want to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.